If a model has several uncertain inputs and you enter an at-risk function such as risk normal in each of their cells, the uncertain inputs are treated as if they are probabilistically independent. However, quantities in the real world are often correlated to some extent, either positively or negatively. If you know that the uncertain inputs are correlated, and you can measure the extent of their correlation, you should account for this correlation in your model by using at-risk's risk-cormat function. It is usually difficult to gauge how much this actually matters. This depends entirely on the specific model. But there is no excuse for assuming independence when you know it isn't realistic. This video illustrates how to do it. The model shown here assumes that you are going to invest certain percentages of your wealth for some period of time in two stocks and a commodity such as gold. The returns are assumed to be normally distributed with given means and standard deviations. And they are fairly highly correlated. The two stocks tend to change in the same direction, which tends to be the opposite direction from the commodity. For now, focus on columns H to J. The quickest way to build this correlation behavior into the model is to first enter the usual risk normal functions, or whatever distributions you want to use, in the uncertain cells in row 14. Then select these cells, the middle group of green cells in columns H to J, and click the Define Correlations button on the at-risk ribbon. This opens the following dialog box, where you can define a correlation matrix. You give the matrix a name, such as Core Matrix 1. You specify the location for it on the spreadsheet. And you specify the correlations. Actually, only those below the diagonal are required by typing numbers in the boxes. So stocks 1 and 2 are highly positively correlated, and gold is negatively correlated with the two stocks. By the way, if the dialog box doesn't look like this when you open it, you probably forgot to select the input cells first, which is a common mistake. In this case, you can cancel out, select the input cells, and try again. When you click OK, the model changes automatically. It now includes the correlation matrix in columns H to J, and the formulas in columns H to J of row 14 now include the risk cormat functions. For example, the original formula in I14 was the same as in cell D14, just the risk normal. Now it includes a third argument, the risk cormat function. The last two, right here, indicates that this is the second of the three correlated variables. The formulas in H14 and J14 are similar, but they have indexes 1 and 3, meaning that they are the first and third correlated variables. 1 and 3. If you prefer, you can skip the Define Correlations dialog box and type the formulas directly, but this will probably take a little more time and increase the chance of making a mistake. If you do it this way, you should first enter the correlations you want directly into cells, optionally range name the correlation matrix something like Core Matrix 1, and then enter the entire formulas, including risk cormat, in the uncertain cells. Note that there are 3 sets of asset returns in the model, just for comparison. Those on the left are for the case of independent returns, so there is no correlation matrix. Those on the right are for the case where the minus signs have been omitted from the correlations. Now all returns will be positively correlated. I will generate its correlation matrix and its risk cormat functions in the same way as before. plus 0.6, and plus 0.7. Before continuing, it helps to know, at least conceptually, what at-risk does when it runs a simulation with correlated inputs. When it runs, say, 5,000 iterations of a simulation, it first generates 5,000 random values for each of the correlated variables from the specified distributions, in this case, the normal distributions. Then it shuffles or rearranges these sets of 5,000 numbers so that they have the desired correlations. For example, the 5,000 stock 1 and 5,000 stock 2 returns are shuffled in such a way that low values tend to be paired with low values, and high values tend to be paired with high values. Now I will run the simulation for 5,000 iterations. Here are the histograms of the portfolio returns. There is independence, there is negative and positive correlations, and there are all positive correlations. The corresponding summary statistics found with at-risk statistical functions are shown below. They allow you to compare the three cases. First, note that the three mean returns are almost identical. This is no coincidence. Averages aren't affected by the shuffling just described. However, the correlations do affect the variability of the returns. As you can see from the standard deviations and the 5th and 95th percentiles, the portfolio return distribution with positive and negative correlations is less spread out than the distribution with independent returns. And the opposite is true for the model with all positive correlations. It's more spread out. This might not have been immediately apparent from the histograms, but they have different scales on the horizontal axis, which makes them harder to compare. The all positive correlations model is the case of putting all your eggs in one basket, whereas the positive negative correlation model applies to the investor who diversifies. The diversifier has a safer portfolio, whereas the all eggs in one basket investor has more upside potential, but also more downside risk. For each of these models, you can check the actual correlations of the simulated data. To do so, select any cell in a correlation matrix and click the Browse Results button. You see a matrix of scatter plots of the correlated values, along with their sample correlations. Of course, the sample correlation should be close to the correlations you specified. Any differences are the results of sampling error, and these differences will decrease with more iterations. Before concluding this video, I will point out one other feature of at-risk's defined correlations tool. There are some sets of correlations that aren't valid, even though all of their values are between -1 and +1. They are invalid in the sense that no data set could ever have these correlations. I will illustrate one possibility, using the correlations -1, 0.9, and 0.9. When I click this button right here, it checks for matrix consistency. If I say check matrix consistency, I get this dialog telling me that it is not consistent. If I click yes, at-risk will do its best to find values reasonably close to the ones I entered, and in this case it will use the values shown. Actually, at-risk has an option that gives you more control on how the correlations are adjusted, but I won't cover them here. Summarizing, the point of this example is that when it makes realistic sense that uncertain inputs are correlated, either positively or negatively, It is important to build this behavior into the model explicitly with at-risk's risk-hormat function. If you don't, and instead assume independence, the results can be quite misleading.